In Chapter 12, what we're going to be looking at is density and scaling. So pretty easy stuff. So the idea is we are actually going to skip a number of things in this chapter. So there's cool stuff we don't cover, like domes. And of course, I couldn't resist covering it a little bit. But the idea is with a dome or an arch that the forces, so, you can imagine that you have lots of bricks up here on top of this archway. Those forces get redistributed sideways along the arch. And usually you have to have some extra buttresses to resist the movement of the building sideways, where then it would collapse. So that used to make walls very, very thick. And so in the Middle Ages, they figured out how to make what are called flying buttresses. So instead of building walls thick like this, they made the interior walls thin. And so this would be inside, say, a great cathedral or something, a big, tall building. And you could have your stained glass windows because the walls were thin. And you wouldn't have to have all that reinforcement. The reinforcement would be taken off to the side, to the flying buttresses that would be off to the side. And so you could have tall, light buildings, and the forces would go out into those extra buttresses. So anyway, so some amazing buildings were built with these flying buttresses that take the forces out to the side of these cathedrals. So you could have very tall buildings, and there would be all this room for stained glass and stuff because you didn't need strong, as the walls to be as strong on the interior. Here's a cartoon. So people learned how to make many different types of arches, and eventually they came across a design called a catenary arch. Now the catenary arch is the opposite shape of a chain that's held, by 2 points. Gravity is pulling on each link in the chain. And so the catenary arch acts the same way. Gravity is pulling down on each part of it. And it comes to a lovely curve that takes most of that force and pushes it down into the earth. Not much goes sideways. And so that is what the St. Louis Arch is. If you ever go to St. Louis and you get to go up into the arch, there's an elevator that takes you up. And there's an observation on the top, an observation windows. And it's a freestanding arch, which you can do with this catenary arch design. Okay, so that's stuff we're not covering. So let's look at density. So we talked a little bit about the fact that different materials will have different densities in the last chapter. Density is mass divided by volume. And so usually, of course, we're going to use grams or kilograms for mass. For volume, we're going to use centimeters cubed or meters cubed. So we'll often use grams per centimeter cubed in the lab, or we'll be using kilograms per meter cubed for larger things and for calculations. So mercury has a density of 13.6 grams per centimeter cubed, and water has a density of 1 gram per centimeter cubed. So we talked about water before, and the definition of a gram comes from 1 centimeter cubed. We were talking the metric system. 1 centimeter cubed of water has a mass of 1 gram. So the density of water is 1 gram per centimeter cubed. Now, another thing, of course, is remember that a centimeter cubed is also a milliliter. And if you're like in a hospital setting or something, it's hard to say centimeter cubed and it's hard to say milliliter. So they shortened it to cc, cubic centimeter, 1 cc. Okay, so those are all equivalent to each other. And if it's water, then it has a mass of 1 gram. So mercury, which is a liquid metal, has a density of 13.6 grams per centimeter cubed. Now, we talked about how density was one of the properties that Mendeleev used to identify materials. And you can have densities of solids, liquids, or gases. One way to think about it is how compact things are, how much mass they have in a certain space. And this is why we say some materials are heavy. What we're usually saying is they're more dense. And other materials we'll say are light. So we'll say, oh, bamboo is light. Well, it's light for its size, right? For its volume. And iron is heavy for its volume. So anyway, here we've got a whole bunch of cubes that are the same size, but because they have different densities, they have different masses. Whereas over here, I showed you how I had blocks that all had the same mass, but they have different densities, so they have to be different sizes. The larger they are, then that's because they can have a larger volume because their mass is smaller. Whereas the smallest block here is tungsten, which is quite heavy for its size because it is the most dense there. Tungsten has the symbol W, by the way. There's also some titanium there, which was closer to the aluminum. Titanium is known for its lightness. It's low density also. Strong, but low in density. Okay, so now we need a symbol for density. We can't use D because we've already used that for distance. So they use this letter, this Greek letter rho, which does in fact look like a D, a kind of upside down, right? So rho is the letter for density. And here's a table of some densities. Now, the density list here is in kilograms per meter cubed. To make it grams per centimeter cubed, you just have to divide by 1,000. So we've got water here is 1,000 kilograms per meter cubed. And so divide by 1,000, that's why it's 1 gram per centimeter cubed, right? And mercury would be 13.6. And over here in our solids, iron is 7.87 grams per centimeter cubed. And you can see how aluminum is much less dense at 2.7. And you can also see how lead is much more dense at 11.3. But what you may not have realized was lead is not the most dense substance in the universe. And so you can see how gold is more dense than even uranium. Gold has a density of 19.3 grams per centimeter cubed. It is nearly twice as dense as the lead. Okay, so anyway, and you can see platinum is more dense even than gold. All right, so anyway, so some materials have a greater density. The greater the density, then for a certain mass, they can take up less volume. Now, if we want to calculate the density of something, so let's say we have a material and we're trying to identify it maybe. And let's say the density, we don't know, but we have the mass. And let's say the mass is 16.2. And we'll make that, that's grams. And then we've got a volume of 2.3. And that's going to be in centimeters cubed. So to find the density, mass divided by volume, and so 16.2 over 2.3 is going to equal 16.2 divided by 2.3 equals 7.04. Okay, so then we might go look at our density table and say, okay, well, what material might this be? Okay, so 7.04, we don't have anything exactly that, but tin is the closest. So we might say, okay, well, maybe it's tin. All right, so that would help us to identify this material. That's the closest one on this list. But that list isn't complete. Remember, titanium's not on there, and that has a density closer to aluminum. Okay, but probably not 7. All right, so weight density, of course, is something that we use in the United States often because we don't use mass. So weight density is weight over volume. And so we use pounds per cubic foot. So if you're ever putting in a swim pool or a hot tub on a deck, you might calculate the mass of the the swim pool, or I'm sorry, the hot tub, to see if it's going to cause problems with the deck. Okay, so the density of salt water is 64 pounds per cubic feet, and fresh water is 62.4 pounds per cubic feet. Because yes, salt water is more dense than fresh water. And there's a great video which is on aerosols. So anyway, so the least dense material, aerosols, and that's a really good video. I'll try to put a link in for you guys. All right, so the thing is, if you're trying to figure out the mass, since density is mass divided by volume, then turn it around, mass is going to be equal to density times volume. Okay, so let's do a calculation of that. Here we've got this student, and they are visiting Fort Knox, and they decide to take out a loan from the government, throw a couple of gold bars in their backpack. And so the question is, what would be the mass of a backpack full of gold that is 20 centimeters by 30 centimeters by 10 centimeters? Okay, so our backpack is 20 by 30 by 10. So 30 here, 20 there, 10 there. So we can get the volume of the backpack. Length times width times height. So we get 30 times 20 times 10 or something. And that's going to come out to 6,000. And that should come out in centimeters cubed, right? We're doing this in centimeters. Okay, we've got the volume. And the question is, what's the mass? Well, we've got part of what we need. As I said, since density is mass divided by volume, the mass is going to be density times volume. And this is gold. So we can look up gold on our table. And the density of gold was 19.3 grams per centimeter cubed. Now we'll want to use that because we're using centimeters cubed, okay? So we don't want to use the 19,000 one because we're not using meters at the moment. So you look at your problem. Is your problem using meters? Then you want to use the density in kilograms per meter cubed. Is your problem got centimeters? Then use the grams per centimeter cubed. Okay, so we need 19.3. So that's our density. 19.3 grams per centimeter cubed. And then we're going to multiply that by our volume of 6,000 centimeters cubed. And so what we're going to get is 6,000 times 19.3 is 115,800. And what are the units? Well, because we we can cancel out the centimeters cubed, right? That leaves us with grams. So this is going to come out as a mass, as we would expect. Now, is that a lot? Well, let's shift it to kilograms. So we can move the decimal point 3 times. The mass is going to be 100, and let's say 16 kilograms, which is the mass of a fairly heavy person, right? We said that people were often about 50 to 70 to 100 kilograms, and that made them 500 newtons and so on. So anyway, so this is like a pretty big person, maybe 200 pounds or something, and that would be in your backpack. So it's a lot to carry. Gold bars are often smaller than regular bricks. That's how they're usually made. So a gold bar might be this big compared to a building brick because the gold bars are so much heavier, more dense, right? So heavier for their size. So anyway, so yes, so his backpack full of gold, even though it's not a very big backpack, would probably be kind of heavy for him to carry. And certainly if he was running away from the guards, that would be too heavy. Okay, the other part of this chapter that we're covering is scaling. Scaling is the idea that as you make something larger or smaller, that's called scaling up or scaling down, what happens is that you have properties that come into play, because just changing the length also changes the volume and the weight of the object that you're scaling up and down. And those can have effects on the structure that you may not intend. Okay, so scaling is the study of how the size and shape of an object affects the relationships between the weight, strength, and other physical characteristics. And that's in the end, we're going to talk about why elephants have thick legs, but ants can have skinny little legs, or spiders. Theirs are really skinny. That's because of the scaling up phenomena. Okay, so let's look at this cube here. We have a cube that is 1 centimeter on each side to start with. Okay, so it's 1 centimeter on each side. And then that makes the length of a side 1 centimeter. The cross-sectional area would be 1 by 1, so that's going to be 1 centimeter squared. The volume is 1 centimeter cubed. And the mass, if this was filled with water, would be 1 gram, right? So this is a substance with the same density as water. Okay, then we scale it up. When we scale it up to 2 centimeters on each side, you might think, well, I've just doubled everything, right? But you would be wrong, because the area is now 2 by 2, which makes 4. And the volume is now 2 by 2 by 2, which makes 8. So instead of just doubling everything, you've doubled the length of a side, but the area has gone up by 4. The volume's gone up by 8. And because now there is more volume, 8 times volume, then that's 8 times as much mass. So keep going. What happens if you multiply by 3? Okay, 3 times more. And each side now has an area of 3 times 3, which would be 9. And the volume is now 3 by 3 by 3, which is 27. And since mass goes along with volume, 27. And so on and so forth. And so you can see what's happening here is that all you intend maybe is to change the length, but everything else is changing by more. And of course, you can see hopefully the mathematics here. If I make the length of side x that I've multiplied, then what happens is the area goes as x squared, and the volume and mass go as x cubed, right? Because area is side by side, right? Volume is side by side by side. So length by length by length x cubed. Now, how do these relate to living creatures? Well, strength is a function of area, but mass and weight are a function of volume. So what happens if you suddenly have a dog that is 3 times larger, okay, then the dog will be 3 times stronger. The cross-sectional area of their muscles might be 3 times stronger. But the dog now has to carry 27 times more weight, right? So 3 squared, I'm sorry, so the strength would be 9 times greater. I don't know why I said 3 there. So the length is 3 times greater, but the area, which is the strength, is 9 times greater, and the mass and weight is 3 cubed. That's going to be 27 times greater. So the problem is they may be stronger, but are they strong enough to carry that weight? And so what has to happen is as an animal becomes a larger type animal, like a mouse turns into an elephant, well, they can't keep their little cute mouse legs. They have to have bigger, bulkier elephant type legs. So if the size has gone up 100 times, then that means the mass is 100 times 100 times 100. So all of a sudden your mouse would no longer be able to walk around on skinny little legs. So anyway, yeah, so this is why smaller animals can often have tiny little legs. But bigger animals, they've got to take care of that density, that bulk that now makes up themselves. Okay, now another thing that's important is the skin surface area. That also goes up as area. And the thing is that skin surface area helps you to get rid of heat. Okay, so heat radiation is part of your skin surface area. But the heat produced depends on your weight and your mass, because all those cells need to metabolize energy. So what happens is that you have a lot more heat that's produced. And so animals can actually get to the point where they're so large that they have trouble getting rid of heat. And that's actually true for elephants. It's true for lions. Lions can have short bursts of activity, but then they have to sit and pant for a long time. Okay, because they don't have a very good way of getting rid of heat like dogs. So elephants, what they do is they actually have ears that they flap, and those help them get rid of heat. So this is showing the thermal temperature, and you can see the ears are cooler, whereas the trunk is quite warm. But the idea is that the ears have all these veins in them, and those veins carry heat so that it's in contact with the air here, and it can radiate out. So those are like, yeah, elephant radiators. Monkeys, what they do is they actually use their tails. Their tails are the same thing. Tails aren't just for grabbing onto stuff. The tails actually have extra veins in them, and they help them get rid of heat. Okay, so another thing is that the skin surface area, that has to do with food digestion too, because your stomach is lined with epithelial tissue, which is skin type tissue. And the area that's available of your stomach, it determines how much food you can digest. But how much food is required depends on your volume. So again, you might be 9 times greater in area, which would be 9 times more food digestion that you can do, but you need 27 times more food digested. So how do animals adapt to that? Larger animals, sometimes they try to use less energy. So they will sit very still for long periods. So like a spider, a tarantula will wait, okay, till the right moment to grab something. And so they often have more time between meals, okay, because they try to move very slowly and use less energy. So anyway, so yeah, so digestion and food being required, those two things may be off. And also, of course, as we get larger, we get fancier and fancier digestive systems. So what did humans do? We're big, but what we have is a very, very fancy digestive system with a long intestine, right? So we increased our capacity to digest. Same thing with lungs. Lungs, the surface area of it is what is takes in the available oxygen, but how much oxygen you need depends on how much metabolism is going on. So how many sugars you are burning in your body. And so again, the volume would be is 27 times greater, so you need 27 times more oxygen because each cell needs some oxygen, but you may only be taking in 9 times as much. So what happens is that again, as animals got larger, a spider has just a simple air sac that it can take oxygen in. Some insects just breathe through their skin. But of course, we have a very fancy lung with alveolas, I believe they're called, little curly areas. We increase the blood flows through and is able to increase the amount of oxygen that comes in and is able to get to the blood by having a very, very fancy system inside. So anyway, so yes, so our bodies of animals have to adjust. If they're small, they can get away with a lot of stuff. But if they're large, then these things have to be designed for larger animals. So this is why you will probably never actually find a giant spider, at least not one that looks like a traditional spider. The legs would have to be much thicker to carry the mass of the spider. And by the way, Shelob was the name of the spider in Lord of the Rings. They didn't actually say its name, but it had a name. Okay. So anyway, so people, we adjust our temperature. We have lots of places where we radiate heat, a lot in the top of our head and our feet and the rest of our skin. So when we want to keep heat in, we cover ourselves up with clothing, right? And you can see how these people, the red is where they're radiating energy away, and the blue and green is where you don't see the energy radiating because it's been trapped by the clothing. Animals also can adjust their body. So here's the cat thermometer. A cat will curl up when it's cold. When it's hot, they stretch out so that more air can reach parts of their body. Now, another thing that's in this chapter is the idea of the surface area to volume ratio. So in our first box here, it's 1 by 1 by 1 by 1. Anyway, it is, when you unfold it, there are 6 sides. So the surface area is 6 centimeters cubed. The volume would just be 1. Okay, centimeter cubed. Okay, now when you make it larger, so double it, now it's got a surface area of 24. The volume is 8. So now the surface area to volume ratio is 3 to 1. So here it was 6 to 1. So what does that mean? Well, the smaller object had more surface area. That's more places where heat could be radiated, if you're thinking of an animal, or a building. That is also where oxygen could come in, right? So the smaller it is there, then you've got a better ratio. And then we've got our object getting even larger, 3 by 3 by 3. And now the surface area is 54. The volume is 27. And now the surface area to volume ratio is only 2 to 1. So for each 1 centimeter cubed volume, there's only 2 centimeters squared of surface area where there could be a flow of heat or materials in or out. So anyway, so this is why as objects get larger, again, they have to adjust for that surface area loss. Now, one of the ways to do that is to change things. So like animals that are in cold areas, they want to reduce that surface area. So ears, unlike an elephant who wants to radiate heat through its ears, the ears of these animals are very usually smaller, right? And they also make a rounded body because the rounder things are, that actually has the best surface area to volume ratio of any shape, so better than a cube. So a sphere has a better ratio. And so that means if you want to keep heat from leaving, then a sphere is the best one to have. That's the least surface area. So the ancient igloo was actually a really good design. So people in the Northwest are often building square houses now. Well, square houses actually are not as efficient in terms of heat energy. And if you live in so that's living in the north. If you live somewhere like out west, people build ranch houses. What is the ranch house like? Long, right? Everything's stretched out, and that allows more heat to radiate out. Okay, more contact with air. So anyway, so yeah, so that's the difference between living in the north and living in the west. And so living in some place like we do here in Chicago, I live in a ranch house, but really probably the best shape to have is like a two-story house. Okay. And then what happens is that that's pretty good at retaining, since we heat in the winter, and in the summer there's not as much surface area, and any heat that goes up, it can go up into a second floor. So if you're heating a house, and so anyway, so yeah, so that's probably what we should have ideally in this area, is something like that, where it's closer to round than it is stretched out. Okay, now surface area does affect the rate of reaction. So when you've got coal burning, for instance, you can have one big lump of coal, or you can have many tiny lumps of coal. Same mass of coal, but what's the difference? Well, the difference is that when you've got more space, then more oxygen can get in between, because you now have a larger surface area. And so now with the oxygen coming in there, it will burn better. So we don't usually burn just one big lump of coal, right? We have many smaller charcoal briquettes. Um, and the same thing when you're doing a chemical reaction. You don't want to just put one lump of material in your beaker. No, you pour in a powder that will have lots of surface area. So anyway, so the same thing happens with rocks. They get dissolved by acid rain, and that will happen faster if you've got more surface area. So if the rocks has cracks. And of course, this can also occur for anything burning. The smaller the pieces, like we were talking about coal, but also, when you're out at a campfire, you don't just start with the big logs. You start with the kindling. The kindling is smaller pieces, and that will make a better reaction. But the smaller they are, the more likely it could actually explode. The chemical reaction could be so fast that the gases that are produced knock down walls. So, so you can have things like coal or grain dust that actually explode. And so, a dust explosion, we've got sawdust, a coal mill, grain silo. Um, these things actually blow up. If you can burn it, like you burn your toast, then it can also blow up. Okay, so the wheat can blow up if you've got wheat dust. Okay, so one of the best videos of this is the YouTube video, Creamer Cannon. So let's see if I can get that going, and I'll just tack that on here. Okay, so I'm going to see if I can get it started. Yep, let's see. Put my pointer on. Okay. Okay, and I have to go switch to a different screen here. Okay, and if you need to just find this on YouTube for yourself, just type in Mythbusters Creamer Cannon, and you'll easily be able to find it.
Waiters always look at me and think that I'm going to have a little salad, maybe a soup, and that'll be the whole meal. And when I do my actual order, this priceless look on their face, like they can't believe. Like, is someone else coming? I love food. I eat a ton of food because food is my fuel. But without a healthy gut, food is not your fuel.
Sorry, we're going to skip this ad. There we go.
Goes right, and that stuff goes up in the air, and it actually ignites. We could set this whole hillside on fire.
I'm either expecting to see a much bigger mushroom cloud of fire, or because it's heavier, we're going to see, and it's going to catch on fire, and then we're going to stand there and watch it burn out. Hopefully, choice A.
Grant slowly builds the air pressure to 120. In you go. Then Tori sets the spark. The mass of the creamer in relation to the volume of air is crucial. This could either be a blast or a burn. All right,
okay, let's go back here for just a second. Okay, so what are they doing here? So what they have is they have a container of compressed air, and
choice A.
Grant slowly builds the air pressure to 120.
So the compressed air is going to go into this blue container. That's the one that contains coffee creamer, because just like it can burn. And so then what they're doing is they're placing on top of this creamer.
Here we're going to see.
Okay, so there's the blue container. This has creamer. This has creamer up here in the yellow part. And they've just put a flare in there. Now, it didn't start burning with just the flare in there because the creamer's packed in. We have to let the creamer particles separate so air can get in between them so that it will catch on fire. And so that's what the air is going to do, is it's going to give it a chance to spread out.
And it's going to catch on fire, and then we're going to stand there and watch it burn out. Hopefully, choice A.
Grant slowly builds the air pressure to 120. In you go. Then Tori sets the spark. The mass of the creamer in relation to the volume of air is crucial. This could either be a blast or a burn.
All right, fire this puppy up. All right, here we go. Non-dairy creamer cannon in 3, 2, 1. That was frightening!
Terrifying!
Did you get that on high speed?
Yeah, we did remember to push the on button on the off chance that this might be one of the biggest fireballs ever.
This was frightening. I mean, seriously, there was a moment where I'm like, oh crap, this was a bad idea.
All I heard in my head was run, and I started up the hill as fast as I could go, and I'm still on a little bit of an adrenaline buzz right now.
Dude, you gotta feel this. It's like the top of a creme brulee.
Oh my god.
I think you need a new camera.
Can we take that off? Still rolling? Oh, look at that.
Oh, whoa! Saved it!
Okay, so anyway, so as you can see, when you make it into small enough pieces, it burns much more easily. All right, so I will see you next time. And yes, there's a little bit more of this video, but yeah. So as I said, you can find it on YouTube under Creamer Cannon with Mythbusters. Okay, see you later.